As the problems you're trying to solve in programs grow more complex, often you want more flexible ways of organizing your data in your programs. Up until now, we've been using lists, which are sequences of values that you can look up by their index. And that index is an integer starting from 0 and increasing linearly, right? But that's a pretty rigid structure. What if we wanted to be able to look up our data and organize our data with some other indexing strategy than just starting from 0 and working our way up? And a Python's dictionary is going to give us the ability to do that. The motivation for calling this data structure a dictionary is because we can relate it to how you think of a dictionary in the real world, right? A dictionary associates some word with some definition. And in Python, we're going to call the word a key. This is the key that we're able to look something up by. And we're going to call the definition a value, whatever value is associated with it. And so if we were to use a dictionary like a list, we would think of the key as the index and the value as whatever item was stored at that index. But with dictionaries, we have much more flexibility. And to demonstrate that, let's just jump right into an example in the REPL. So I'd encourage you to join me and open up a Python REPL. And we're going to go ahead and import the type of a dictionary. So from typing, import dictionary, right? And when we specify a dictionary type, like if we want to specify the type of some variable that will store a dictionary, we're going to need to give two specific concrete types, one to specify the key and the other the value. So let's imagine we're trying to organize some data about a team, a roster, where players have jersey numbers, and each player has their own unique jersey number, and that's going to be associated with the last name of the player. So I might have a team that is a dictionary. And just like a list, we need to provide, well, what types of data does this dictionary store inside of these square brackets? So we're going to say that a dictionary stores an integer as the key, and that's what we're going to be able to look up a player's last name by. And their last name is going to be a string, right? We're going to go ahead and initialize this to an empty dictionary using an empty dictionary literal. Soon we'll look at how could you actually initialize a dictionary to have some starting keys and values in it, or some starting definitions in it. But for now, we're going to start from an empty place and work our way up. So what we've just done is we've established a dictionary that's empty. And I'm going to go ahead and try and visualize what's going on in memory so that you've got a mental model for what's happened. So we've got this team variable, and it's storing a reference to a heap value that is a dictionary from int to string. And we'll look at exactly what that means in just a moment. But what a dictionary is going to have is some entries where there are a key column and a value column. And just for reference, I'm going to actually add some arrows in pink to associate. Integer is saying the key of our dictionary is going to have to be an integer, and the value is going to have to be a string, right? Now we haven't added anything to this dictionary yet. We're going to come back and append some entries or insert some entries in just a moment, right? But this is the starting point for our empty dictionary, okay? So the very first thing we can try doing that would create an error if we tried to do the same thing with a list is we can say, okay, team entry with a key 23 is assigned the string Jordan. And there's no error here. Now remember, if we had tried to do this with a list that was an empty list and we tried to assign to index 23 some new value, we would have had an error that said this is an invalid index. We are out of bounds. Our list doesn't have any items in it yet. We would need to append 24 items in order to be able to work with an index 23, right? Because the list always starts from 0. But with a dictionary, we get to establish whatever keys we want as we do so. And so what this would have the effect of doing in our little memory model over here is inserting a new entry where there's the key 23 and the value string Jordan, right? Now, you might be thinking, well, in a list, we could look up using the list name and some index in the subscription notation. We were able to look up what value is stored at that index. And just the same in a dictionary. You give the name of the dictionary, and then in subscription notation, whatever key you're looking up. And of course, we see that Jordan was the string associated with that key. Now, if we try to look for a key that didn't exist, like 33, we would see a key error, right? And this is similar to a value error. This is saying the key 33 does not exist in this team dictionary, right? But we could associate 33 with Pippin, another member of the championship Bulls team, and try that same expression again, team 33, and see that now Pippin is associated with 33, right? So we could have established here 33 and then the string Pippin, and this is no problem, right? So your dictionary is able to grow as you insert items into it. Now we can change an item that exists in a dictionary by writing to the same key or assigning another value to the same key. So we could say team 23 is actually James, right? And in doing so, this would have overwritten the value previously associated with the key 23 to be James instead, right? You can only have one value per key. The keys that are in a dictionary form a set where each item in that set must be unique. So you can't have duplicate keys in a dictionary, but you can have duplicate values, right? We could have two players whose last name is the same, and that would be fine. In fact, if I wanted to make, for some weird, bizarro reason, the 33 jersey associated with James, that would be fine. And if we were to ask Python to give us a string representation of our dictionary, we could see that the value James can occur in this dictionary twice, but you can only have one key, or you can only have unique keys as a part of your dictionary. You can't have duplicate numbers in this case, or duplicate keys more generally in a dictionary. Great, so now that we've explored this just briefly, I think it's worth setting up a file in VS Code that we can serve as some notes and that we can reproduce some of what we just did together in the REPL, leave some comments, and show some additional capabilities of dictionaries. So we have the sense that we're able to create a dictionary whose keys and values become associated with one another, and we're able to choose the types of those things. So we might choose a different key type or value type, and we'll see an example of that as we get into this. So I'm working in our current classroom example directory structure. So I've got a directory named lessons, and I'm going to go ahead and set up a new file in that directory named ls26 underscore dictionaries.py, right? And the name of that file is here in the tab, and I would encourage you to follow along with this. So we're going to set up a doc comment here that will be some reference examples of using dictionaries. All right. So let's go ahead and recreate what we had just seen before. So we, from typing, import the dictionary class, or the dictionary type that allows us to specify the type of a dictionary. And then we set up a team. We're going to, team was a dictionary where the key type was an integer and the value type was a string. And we initialize with an empty dictionary syntax. We'll look at how we can use pre-fill some values into a dictionary using dictionary literal syntax just in just a moment. So I'm going to go ahead and leave a comment here, which is declare dictionary key type value type. So in this example, int key is int, value is a string, right? Or in other words, we're mapping integer values to strings. So we're mapping integer to string. Great. We can insert new keys. We do that by using subscription notation. So team index 23 is assigned the string Jordan, right? Team index 33 is assigned the string Pippin, and team 91 is assigned the string Rodman. For the purposes of this example, I'm going to actually elevate Rodman, or the number 91 index, to be above Jordan, to show you that the order in which you add your keys and values, and you do this in pairs, right? We're associating the key 91 with the string value Rodman. The order in which you do this doesn't matter. It was just a coincidence that we were doing it in ascending integer order before. It doesn't matter how you insert these. In modern Python, your dictionary does remember the order in which you inserted, and when you iterate through a dictionary, which we'll see in a second, it will reproduce the same order in which you inserted your keys into it. But there's no rule that you have to insert them in any order. We'll see in just a moment that when we try and do a for loop through each of our keys in this dictionary, we'll start from Rodman. Just because we inserted Rodman first. Now, I should note that this is actually something that's unique to Python, and especially newer Python. Generally, the idea of a dictionary, you don't like to assume that there is an ordering. This is just a convenient feature that Python has built into it. All right, so what are some other things we can do with a dictionary? So let's go ahead and try iterating through the keys of a dictionary. So even though a dictionary is not a sequence, right? A sequence, there's a specific order. A dictionary is still what we would call iterable, meaning we can iterate through each of its values one by one. And that means we can use it with a for in loop, right? So we can say for key in team. And by default, when you iterate through a dictionary, you're going to be given each key one by one. So because of what we just mentioned before, you do expect the same order that you inserted your keys to be reproduced as you iterate through them. We would expect this if we print this out. So print the key to be 91, 23, and 33. All right. So I'm going to go ahead and save my work here and open up a REPL. Or a terminal actually, and try running Python M. And then because I stored this in the lessons folder, ls26 dictionaries, that's what we named our module. So this is the package and module name. When we run this, we see that 91, 23, and 33 are printed out, which are the keys that we stored in our dictionary. And you might be thinking, well, how do we get the values? And let's go ahead and add an example of that. So I'm going to add an example, access values by their key. By giving their key in subscription notation. All right. So we can print team, and then we're looking up key. Now we may actually have wanted to name key something other than key. Like we could have named this jersey number, and that for the problem we're modeling here, that would have made more sense. But for the purposes of illustration and just having documentation on dictionaries, for this example, I'm going to leave it as key, but just like we've seen with for in loops, you can name this whatever you'd like. All right, so this is how we would print the key the value associated with that key. So if I tried rerunning that in my terminal, notice that on each line we printed the key followed by the value, right? So just to back up for a moment and think about what we've got here. As opposed to a list where we needed to have every single index in some subsequent order and some item associated with that index, with a dictionary, we're able to plug in whatever keys we want, and we could have a key of, a 10 million. We could have, if we were thinking about this as like social security numbers, we could use a social security number as the key and then a name associated with it. Or in our class, we could think about our student ID or our PID and associate that with names. And those are really big numbers, right? Those are 9-digit, almost a million, almost a billion numbers in a PID that we don't have to store all of the values in a list format in order to work with it. All right, so from here, what we're going to do is look at some other capabilities of a dictionary. So one is we can remove an item with pop. And you tend to do this by the key. So we can pop a specific key, right? So this is very similar to how we did the same operation with a list. So if we were to say, I'm going to set up a variable to show you why pop is called pop. It's not just called remove, because not only are we removing it from the dictionary, but we're also, that method returns the value that's removed and was associated with the key. So I might say booted player is going to be a string. And we know this because this is going to give us back the value that was removed by its key. And we're going to say team.pop, and the key that will pop is, let's say, 91 Rodman. And so now if we were to say print booted player and print team, what we'll see, and let me just scroll that up as the last two lines of output, is that Rodman was the booted player, this value associated with the key that we popped, and team is now the dictionary that has only 2 items in it. So dictionaries, just like lists, are mutable data structures. We are able to change by adding and inserting or overwriting previously inserted values, or even by popping and removing key value pairs from our dictionaries. All right. Another common thing that you want to do is know whether or not your dictionary contains some key. And we can do this very quickly. Trying to determine whether or not your dictionary contains a specific value actually winds up being a more expensive operation, one where you often need to iterate through all of your keys and test yourself whether or not you have a specific value. But typically you should try and organize your problem so that you're not doing that. But it's very fast to look up whether or not your dictionary has some key or not, right? That's a very quick operation. And the way that we do this in Python is we use the in keyword. And I don't want it to be confused with for key in loop or for key in iterable, in this case, for key in team dictionary. If we don't use this with for in, the keyword in is going to test whether or not something is in some other collection. And in this case, we're going to test whether a key is in some team. So we can print 23 in team. And actually, let's use this as part of a Boolean expression, because, or a Boolean conditional. If 23 is in team, then print you have Jordan, right? If 91 in team, print you have Rodman, right? So these are two different if-then statements, and this is a Boolean expression. The in operator is built into the Python language, and for looking up whether a key is contained in a dictionary, this is a very fast operation that you're encouraged to use to test exactly that. So if we try running this, we'll see that we have Jordan, but we don't have Rodman. That would have evaluated to false because we had previously removed Rodman from the team. All right. So those are the most common things that you're going to be likely to do with a dictionary. And just to go over them really quickly, iterating through a dictionary, when you use a dictionary with a for in, you're going to get each key assigned to whatever your for in loop uses as its iterating value or variable. To remove values, that's totally fine. And we can test whether or not specific keys are in a dictionary with the in keyword. So let's look at one more final example to motivate some of the additional flexibility we have with a dictionary, where the key doesn't need to be an integer. We can use a string as our key. Right, so I'm going to change examples here to DNA base pairs. All right. And let's try and write a function that, given a string of base pairs, where we're only going to specify one letter of a base pair. And remember, a base pair in DNA are the ACTG, which are the chemical pairs, which I am not going to try and reproduce from memory because I don't remember the exact words of the DNA base pairs. But ACTG, we know, are the key letters. And when we try and represent DNA in a data format, Often it'll be encoded as a string of one of the two base pairs. They just pick the one that they're indexing off of. So what we can do is set up a function that's going to be def count pairs, and it's going to be given a strand of DNA that's a string, and it's going to return a dictionary where the key is going to be a string, which will be the letter A, C, T, or G, and it's going to be associated with a count of the number of times that particular base pair was encountered in our program. So I'm going to go ahead and set up the counts variable, which will be a dictionary from string to int, and initialize it as empty for the time being, and go ahead and return counts. Just so we've got a skeleton function here. That is a valid implementation. If we were to try running it, we would have no problem. But we still have more work to do, of course. So to try and illustrate what it is we're going to accomplish here, let's imagine that we call count pairs with an input argument of like A, G, C, T, A, G, right? What we expect to get back is a dictionary. And that dictionary is going to have, and I'm actually going to redirect my arrow up to here, right? It's going to be a dictionary from string to int, where our key and our value are going to be a string and an int respectively, right? And so our keys are going to be the individual letters of our base pair, so A, G, C, T. And our values are going to be the counts of each of these base pairs in our input string. All right, so if we think about how we might do this as a human, we would say, okay, let's look at the string. So there's 1A, 2A, 3A's. So there's 3A's. And for G's, there's 1G, 2G's, right? And for C's, only one. And for T's, only one as well, right? And so we would expect that this function returns to us a dictionary that contains the counts for each of these base pairs and how frequently they occurred in our input string. All right, so let's try writing this example in code. So I mentioned before that you can initialize your dictionaries to have values to begin with, keys and values to begin with. So let's go ahead and do that. I'm going to do this on multiple lines and say my key for A is initially 0. My key has a value that's initially 0. G has a value that's initially 0. And if I want to put these in order, I should have said a C as the second item, and then lastly, T as the fourth, right? So this is dictionary literal syntax, and you will frequently find it valuable to initialize dictionaries in such a way if there are specific keys you want to know have some starting value in them. And so here we're initializing A, C, G, and T because we expect our input string to only contain these specific values. I just noticed I should not have put double quotes around the type string here. I think I was saying string, and when I say string, I have an inclination to just go ahead and double quote. We should have just had the type stir there, not the string stir there. All right, so we know that strings, which DNA is going to be a string, is a sequence of characters. And we know that when we have a sequence, we can use for-in to iterate through each of the items. So when we use for-in on a string, the variable is going to be assigned each subsequent character. Right? So we can say for base pair in DNA. Right? And base pair, again, because you tend to just choose one of the two letters to encode your base pair with, since they're always paired up with one of the other letters, you only choose one of them. There's not an actual, you're not seeing the pair here. You're only seeing one half of the pair, and you can infer the other half because they always bind in the same way. All right, but that's sort of beyond our concerns. I could also name this for char in DNA, right? Because it's going to be each subsequent character. Or even letter, because we know that we're always going to have letters. We're going to assume that someone gives us valid input here, right? So what do? Well, we are trying to increment. We're trying to count up the associated value for that letter in the dictionary, right? So we have counts, which is our dictionary, and our letter is the one that we're trying to increment, and we want to increase that by 1, right? We want to take its current value, add one to it, and store it back in itself. So I'm going to use the relative reassignment operator. That's the addition relative reassignment, right? And then after we've moved through all of the letters in our DNA parameter, we should have a valid count, right? So before we illustrate this, let me just give you a quick run through of how we expect this to work in code, right? So if we're tracing through this, and let's imagine DNA in our frame has an associated string, and we'll just choose a very easy one. Actually, it'll be just A, C, G, T, right? And when we get, that's the parameter DNA, counts is going to be a reference to a dictionary on the heap. And my key column and my value column are going to go ahead and be initialized because we've set up using this dictionary literal syntax here. So this is a dictionary literal, and we're associating the key A and with the value 0, the key C with the value 0, the key G 0, and T 0, right? So this is our initial dictionary table. And when we enter this for loop, we know that letter is going to be associated with each subsequent letter in this DNA input string, right? So we're saying for each letter in DNA, so the first value of letter would be A, right? And so when we go into this loop, we would see, okay, we're talking about the counts dictionary, so counts, and then we look up this given letter, which is A, right? And so we're talking about this specific entry in this dictionary. And because we're using relative reassignment, we're saying, okay, look that value up, it's 0, add 1 to it, and then store that back in itself. So this incremented to 1, right? So we go back to the top of our for loop and we say, okay, are we done processing our for each element in this input? No, we've got to go to A again. So letter is once again A. And when we evaluate this line, we increase A. And so hopefully you're picking up on this picture that becomes a little bit clearer once we move to the next letter, which is going to be C, right? So now letter is inside of this loop C. So we're saying what's counts of C? Well, that's this entry in our dictionary. We want to take the current value 0, increase it by 1, and reassign it back to itself, right? That's what this line of code is doing. So we're moving through and we're effectively just tallying up the counts as we iterate through, G, and that would increase G to be 1, and then we do the same thing with the letter T. So T would increase to be 1. And then when we've iterated through all of our counts, or all of the characters in our DNA string, we're done with the for loop, and all we have left to do is return this dictionary, right? And so this dictionary contains the counts that we've tallied up. All right, so let's try running this and seeing whether or not this is going to work. So I'm going to open up my terminal, and I'm going to begin a Python REPL and say from lessons.ls26 dictionaries import count pairs. Now remember, when we import this in this way, because we didn't use our main if name is main idiom, all of the previous code above this definition is going to run. So we're going to see some output here. All right, oops. All right, I'm going to try this one more time. Python from lessons.ls26 dictionaries import count pairs. There we go. So there was our input, there was all of the code that we had above it being evaluated. But what we've effectively done is we've now loaded this count pairs function that we can now call. So count pairs, and if I give ACGT, AAGG, AGG, right? What we get back is a dictionary that was the result of counting up each of those characters from that input string. Right? And so notice that we have, let me see if I can get this all to fit. Oops. Notice that we're able to organize the problem around what we're trying to keep track of a little bit differently than we would have to do if we only had lists, right? Here we're saying what we care about is counting up these base pair values, which are strings. And in this case, we know that there's only 4 of them, but we could have an arbitrary number of different things that we're counting up, and we'll see an example of that soon. But we're able to index off of that rather than having to maintain maybe 2 lists and relate those 2 lists back to one another. So a dictionary is a handy way to be able to organize data that allows us to look up some value associated or by its key. And this idea of storing key value pairs in a composite data type that you can change over time. We can add new key value pair entries to it. We can remove them. We can change them. Winds up being one of the most powerful data structures you have available just after lists that you'll see many uses for. And in this example, we're counting letters, and that's a very handy application. We could count words. We'll see other examples, like when we have data tables where we have columns that have names and associated values, which are often numbers. Using a dictionary in that case is handy as well. So this is an introduction to the dictionary data type. And next we will look at a real world example of trying to count what are the most frequent letters in Shakespeare's works. And that would be a very difficult problem to solve if you try to do it manually. But now that and it would be pretty cumbersome to solve if you didn't have dictionaries. But with a dictionary, we can do something very similar to what we did in this last example, counting DNA base pairs, but just with letters from Shakespeare's collective works. These are dictionaries. They're one of the most handy and flexible data structures that are useful in many different scenarios when you're working with data in your programs.